Good morning, everybody, and welcome to this Radiocrafts webinar yet again. Since the people are still joining, so I probably will wait approximately 1 minute before I start the proper webinar. So we hope that everybody has found their coffee and are ready. I can start by going through a bit on the household rules. So first of all, my name is Ørjan, and then I see that I have not the correct title in this specific slide, so I do apologize that. I'm Ørjan. We'll keep this webinar to a total 30 minutes plus 10 minutes Q&A session afterwards. Maybe it will be a bit shorter than 30 minutes. You can post questions in the chat window while I'm talking, and I will go through the questions afterwards. And there will be a recorded version of this webinar available on our webpage and our YouTube channel after this webinar. So this is what I will be talking about today. I will give a very short introduction to RIIM. This is not a generic RIIM presentation, but for those of you who found this video on YouTube or somewhere and you wanted to understand what the solution this was really about, there will be a short introduction there. And then we're going to talk about the two use cases which we see are exceptionally good fit for RIIM and explain why they are a good fit and why we see maybe 60-70% of our use cases or customers using RIIM in these two use cases, and then how to achieve these benefits, and also how RIIM then will compare to other solutions. So that's the agenda. So again, one slide on RIIM. So those that are very familiar with RIIM, please have a bit of patience for this one slide. This is RIIM is a mesh network operating at sub-1 gigahertz. That means 868 megahertz, 915. We can also do 433 megahertz. The distance between the nodes in open area, they can typically be 1 kilometer. If you use this long-range variant called HP, then we probably can have 4 kilometers per device between the devices. And of course, since it's a mesh, you don't have to. All nodes doesn't have to have direct radio communication with other. You can use the other nodes as intermediate nodes to forward your message. That is the concept of mesh. It's based on open standards like IEEE 802.15.4G and E. We use Ripple, which is IETF standard. IETF is the same organization that made standards, known standards like TCP/IP and stuff like that. So they are very renowned. 6LoWPAN, we use LPM for multicasting. So basically, it is a lot of different standards put together. Of course, it's auto-forming and auto-healing, meaning that new devices will join the network. If you move a node around, it will be rerouted to other nodes if it loses connection to where it was originally connected. It's IP-based, meaning we use IP packets, UDP, CoAP, and DTLS. We use time-slotted channel hopping, so-called TISH, because it gives extreme high reliability. And we allow that the customer application run inside our modules. So that means that the application which does something, controls something, reads some sensors, whatever it does on a regular basis, or that can all be programmed inside our module. So there's no need for an external controller. So that is the short and quick introduction to RIIM. Of course, if you look at our webpage, you can find a lot more information about it. Then I say that This product has now been on the market since 2019, so 4 years. And we, of course, have many different customers, but we see some trends among our customers to what they use it for. And I will take 2 of those trends and discuss them a bit deeper today. One is the use case called low power mesh. That is identified typically by battery operated routers. Often you can have many devices as well. It doesn't have to be, but we see that as a typical criteria. Also, we see that if you include control, meaning the downlink messages to control the end nodes, and we see the request for reliability. So these are the kind of criteria we typically see for these use cases. Some examples I show here. It can be, for instance, it's typically what we call infrastructure monitoring, meaning that you have something, infrastructure, which spreads over a big geographic area you want to monitor. If you go through the 4 examples here, one is a pipeline. It could be water going through it. It can be gas. It can be other things as well. But obviously, you want to monitor it on different positions to monitor the flow, for instance, to make sure there's no leakage. And of course, you don't have power. There's no electricity grid here. So then we see RIIM being suited for that. The second one, going to the tunnel, is an example for of a mine, which, for instance, you want to monitor gases or other status inside a mine, which is a challenging situation, and you don't necessarily have power all the way there either. The third one is considered the sewers, meaning that you want to monitor the level of water in the sewer system, or maybe the flow or something. So you want to have maybe some gases there as well. So again, it's not much electricity there, so you want to use battery operated devices. And the third one is smart irrigation, where you have a drip irrigation in this case, where you want to control valves and also maybe measure the soil sensors or the soil humidity with soil sensors. So all in all, these 4 use cases is there to illustrate the kind of area where we typically see the battery operated RIIM being of high interest to the customers. So why is that? First of all, with the RIIM SDK 4.0 and later, battery lifetime increased dramatically, meaning that we increased the battery lifetime for the mesh routers by 3 times. And we even added a 150 kilobit per second, a high-speed mode with even lower power consumption, double that again. So for the engineers and the tech nerds, that means that the average or the lowest power consumption went from 120 microamps on the mesh router going to 40 microamps for the 50 kilobit per second variant, and the new 150 kilobit per second mode has as low as 20 microamps as average power consumption. There is other benefits as well. So of course, because we are sub 1 gigahertz, we have very good range. So meaning that, for instance, if we have 20 hops and let's say 2 kilometers per hop, then we can reach 40 kilometers, which is a pretty and we can go in different directions as well. So it's a huge area of I guess it would be a circle of 80 kilometer diameter that we can cover with one network, which is, of course, a tremendous coverage. So we have that. Also, it can also have good coverage in buildings as well, but this is an outdoor example. We can have very long battery lifetime. So with the 20 microamps that we showed on 150 kilobit, you will have a lifetime of 15 years on 2 AA lithium batteries. And that is a very, very long time. So that is also a very good benefit. Also, which is a quality that I sometimes take myself in not mentioning often enough, is the reliability we have in this network. Meaning we are not doing fire and forget like a lot of LP vans, meaning that they just send, that they hope that the packet is received. But the typical LP vans like LoRaWAN and stuff like that they're very happy with 90% delivery rate. That is a good link, they think. For us, that's not a good link. For us, that's a bad link. So all of these networks operate on a typical 99.99% packet delivery rate, which is also very good. And they also offer low latency control. So I will talk a bit about that going forward now. So what does the latency and control mean? Well, control, just to define it, is when we want to control things. For instance, okay, if you're in a mine, have a gas alarm and you want to turn on some flashing red lights to get people out, you want to send a message and you want it to be received, not 1 minute afterwards, but within a couple of seconds. If you wanted to smart irrigation and you have an app to turn on the water flow, then you want to turn on the water flow. You want to look out the window and see, yes, now the irrigation has started. You don't want it to take 10 minutes for that to visualize. So latency is often a trade-off towards battery lifetime. That means that if you enable frequent communication between the devices, battery lifetime will go down, but the latency will also be lower, which is something you want. There are two fundamental ways of doing control. One is the fact that you can have devices poll some central unit saying, hey, is there a message for me? And it can just do this every, for instance, 10 seconds or every 1 minute. But obviously, when you transmit this packet to ask the gateway, do you have a message for me? That requires quite a bit of energy from the battery. The second way to do things is to have a synchronized network, meaning that the gateway and the end device have agreed on this is the time slot that the device will be listening. So this is the time slot. This is the exact time that the gateway has to transmit. So that means that the end node then can just listen for these specific time slots. And listening, being in receive mode, is typically much lower power than transmitting. So being a synchronized network helps in terms of you can do that typical 4 times more often polling if you do it with passive polling than active polling. So why is RIIM the best solution for latency and for low latency and control? We are a synchronized network, and we also have a much higher data rate than low LPWAN, which enables us to also have a very short listening period when we listen. I will show you a curve which explains this a bit more graphically. So what you see here is on the x-axis, I have the response time downlink, meaning how long time does it take to get your message. So basically it's the latency. So 64, this is in seconds. So 64 seconds, some application that is not acceptable, but here it depends on the application again. We have, as shown, the two lowest one are RIIM in 50 kilobit and 150 kilobit. per second, and we show that we can have a downlink response time down to 2 seconds or 4 seconds and still have an extremely low power consumption. You see this lowest one with 150 kilobit per second. It's still it doesn't increase a lot when you go down with having lower latency. While other I've compared here with LoRaWAN based on the calculators which are available from the LoRaWAN organization, and some spreading factor in the middle. If I could use spreading factor 12, I would just be ridiculously high here, so I didn't use that. But I used some more likely spreading factors in the middle, and we see that okay, if your latency is 2 minutes, then you can accept that, and probably LoRaWAN can be an okay solution. But if you want systems which are much more responsive, meaning that they react much quicker to when you want to control something, then you need to then RIIM is a much better solution. And also you see that the battery lifetime on these low latency applications goes or the current consumption shown on the left here goes through the roof pretty quickly when you start to go down to low latency application. So to conclude this, the first part, the low power mesh with battery operated mesh routers is application where we see that the RIIM is an extremely good fit. Again, because of the low power consumption, the low latency and control, and also reliability and the coverage. Combined all these four, then you have a really best-in-class wireless solution. The other application that we also see a great interest in is what we call high throughput mesh. That means typically there are many devices, and the total amount of data coming to the gateway is high. So the total average data amount being high is I guess, a relative term. Some may think, oh, okay, you get 1,000 sensor readings per second. No, that's not realistic for for these type of, even for RIIM in this type of solution. So the typical high data amount could be something like 1 packet per second, 2 packets per second, maybe even 1 packet every second is a high data amount for this wireless solution. And but they also want to combine our use cases here. Typically want to combine these many devices with a lot of data with a reliable solution. So they mean they want every packet to arrive. Some applications where we see this being the case, these cases are not battery operated typically. They can have battery operated sensors, but the routers are typically mains operated. Solar is a big segment, being, for instance, controlling DC combiners or trackers or even inverters in some cases. We have industrial solutions shown at the top right here. It could be what we call submetering, that you want to measure the amount of current used or power used in each machine. It could be vibration analysis or something like that. But again, many devices and a lot of data gathered to one point is the key here. The third one is supposed to illustrate a smart city. Again, many devices and a lot of data. That's the kind of cue here. And we also have electricity metering, where we see this not typically in Europe, but maybe in Asia. It's more typical to use radio mesh to gather the data and thereby generating a lot of data. So high throughput mesh. One of the things we see a lot of customers use today is the fact that they use active, they poll the sensors. What does this mean? Here we are talking about polling, meaning that the gateway send out a request to each sensor saying, hey, do you have some data? This is typically because customers are used to using wired solutions like Modbus, and therefore they use, they easily go into this polling mode. What's also good with the polling mode is that you prevent several sensors from sending at the same time, and thereby you can reduce the collisions on radio. But realistically, we see customers using polling via mesh. They typically end up with a poll each one device per 6 seconds or something like that. Maybe a typical 6, 7, 8 seconds between each poll. The best you can do, I think, is 1 packet every 2 seconds. So that means that that's kind of a limit to how much data you can get into the gateway with polling. You can also poll data from the sensors using RIIM, but with RIIM you also, because we are a mesh network, because we use retransmissions on each hop, because we have this time-slotted channel hopping, we can have the data, the sensors push the sensor readings up through the system instead of polling it. And we can support up to 5 packets per second of data being delivered to the gateway. When we say we can, that's the average we can accept. Of course, in a real network, if you have 100, 200 sensors, you could, and they're sending at a random time. It could also be that within 1 specific second, you get 10 packets. But the purpose here is that we have enough buffers in our mesh that we can kind of handle that 10 packets for that given second by spreading them out, so they will then come a bit later, some of the packets. So we will not lose them, but we will basically, so we can still handle more packets within a given second, but on average, we see a limitation in approximately 5 packets per second. But this is 10 times more data than we get with polling. So let me show you 2 stories here. One story is about 50 solar trackers, each reporting every 50 bytes of data every 8 minutes. This gives an average of 0.1 packets approximately per second to the gateway. And in that case, of course, RIIM will work, but also the lowest rate, for instance, of LoRaWAN might be okay. 98% is for me a guesstimate, but it's maybe a bit even optimistic. But again, this is we still see the difference. But then what happens if you increase this number? So this is going to 350 solar trackers in one network, and each reporting 50 bytes every 2 minutes. This gives an average of 2.9 packets received per second to the gateway. And we see that with RIIM, we are still getting 99.99% delivery rate, which is superb, because it is it means that you can trust your data much more. And of course, with LoRaWAN spreading factor 7, which is the shortest of these LoRa modes, you will Scientific articles show that you will get approximately 75%. This is because all these nodes will then, when the packets from the LoRaWAN devices collide, they will interfere with each other, and basically you will have a packet being lost. And spreading factor 12, you will get 1 to 3% of the packet. So basically that is not possible to use at all. So yeah, why do we see customers using RIIM for these high throughput or high data solutions? We can handle up to 5 packets per second to the gateway without any congestion. We can do that still having a very high reliability. And the final one, which is important because we see other mesh solution doesn't support it, like Vysen, is the fact that because we do adaptive frequency agility, this is the fact that we go away, identify bad channels and move away from them. And also we listen before each packet are being sent. And if there's noise on the channel, we kind of back off and wait a bit to maybe find a new frequency and a new time to send the packet. Because we do these kind of things, we are allowed, according to the EU regulation, the RED directive and the standards used there, we're allowed to send a much higher duty cycle. So that means that we are, and in this high throughput mesh, typically the devices close to the gateway, which have to forward messages from the entire system, they are requiring, they are typically using they're transmitting more than 1% of the time. And if you don't have this AFA, then you are basically violating the CE rules, and somebody can come and tell you to stop your network. So that's not something you want. So now we have talked about both the low power solution of RIIM, and we've talked about this high throughput solution with RIIM. Obviously, the first one, it's optimized for the battery lifetime, and the second is optimized for the throughput. So to use RIIM in these two use cases, RIIM has to be set up slightly different. I didn't want to go into all the nitty-gritty details on that in this webinar, because this is also for a bit, not just the engineers who are implementing it, but it's also for higher level project leaders and stuff like that. But we are coming with a new application note which will go into details on how to optimize RIIM for these high throughput solutions, so that you can easily copy those settings from the application notes to get your high throughput or low power solution working very easily. Okay, so then it's been 29 minutes, so we are right on time. I have tried to look at the chat window. Yes, we have one question from Magnus. I can read it out for everybody. As I heard you talk today, you focused on TISH only. All nodes are routers where some may sleep, and not on the single channel options where you can have many sleepy end nodes to send data. With the latter, even less power is consumed than with TISH. Your thoughts? Yes, so what Magnus is referring to is the fact that in a single channel mode, which is a different mode of RIIM, you can have a mesh network of mesh router, which all are mains operated. So meaning they can use a lot of, they can basically use as much power as they want to. And then you can have what is called leaf nodes, which then are not acting as part of the mesh, but they are kind of end nodes just sending data to the mesh routers. And in that case, of course, as Magnus points out, these leaf nodes can then be even lower power because they are based all the way down to 4.7 microamps. So they are then 4 times less again. So that is for me like a third use case, because then you are combining these this mains operated mesh with these really low power sensors. So for me, that's just a third use case in addition to the 2 use cases I've discussed today. And obviously for that application, yeah, first of all, you need to have the mains powered for the mesh itself, and the sensors which are battery operated. I'm not sure what if that answers Magnus' question, but obviously if I look at the if I'm thinking about some of the use cases like monitoring in the sewer, you don't really have the availability to put up mains operated mesh routers. So the entire, for these low power options we basically have to have battery operated mesh routers as well. Andrea asks, 5 packets per second means that you support up to 30 kilobit packets each 250 millisecond. I'm not sure I understand the question, Andrea. Maybe you can clarify a bit. The max packet is on physical level is 128 bytes at least. I'm not sure exactly what it is in LoRa. I think it depends a bit on the spreading factor and protocol and everything. I don't know. Yeah, I guess Andre has to clarify a bit more what the 30 kilobit packets each 250 millisecond means. I guess I'm waiting to see if Andre clarifies. There were no other packets. Sorry, and no other questions as far as I see. So if there's no other questions, I would like to thank you all for listening in. I hope this was good in terms of understanding some of the use cases that we see that RIIM has an exceptionally good fit. And of course, as Magnus says, there is other applications and other use cases, like I know Magnus is using it for. I didn't want to talk too much about Magnus' application because I didn't want to spill his his secrets here. But of course, he is using it as a basically replacement for Zigbee with better range, and that is of course one option as well. So this does not mean that RIIM is limited to these 2 use cases, but as I said, we have seen the 2 use cases I talked about today being what I call exceptionally good fit, meaning that we have a clear advantage compared to the technologies in the field. I also have another question from Miro. Does it work with only one-way common? Not quite sure. So it is a question from Miro here. does it work with only one-way communication from sensor towards the network? All the communication is acknowledged in our system, meaning that if you have a sensor, it will send it packet and get an acknowledgement and have retransmissions. So there's no, but you don't really need to send any data to the sensor's application data. So you can only send application data up, but on the physical level, on the radio level, there will be acknowledgements, because unless, of course, you can do something called broadcast, meaning that you just broadcast it out to all the neighbors and then do not have an acknowledgement of that packet, but then you lose the reliability you get that we have with doing acknowledgement and retransmission. And that's partly why we can get 99.99% reliability. We get those numbers, by the way, 99.99% reliability, even if we can put it into a simulator. We can say, we can force the simulator to lose every, like 5% of the packets. And even though we tell the simulator to take random 5% of the packet and just drop them, say that you didn't receive them, we still get a 99.99% reliability from at the system level, because of retransmitting on different channels, on different frequencies. So it's not that we don't lose packets. There will be packet loss also in the RIIM network, because all radios or wireless systems will lose some packets. So we're not trying to do magic here. There is interference out there. There are cellular systems, there are other sub-1 GHz radios. So obviously we will lose a packet, but again, losing 5% of the packets has little or no influences on the reliability we get out. Okay, I think that's it. So I will thank you again. Thank you all for joining. And if you need more information, you can find a lot more information on the Radiocrafts webpage. So thank you very much.